Everyone's tired. Good morning. All right, so you had your test last day. I have not had a chance to look at them because I'm marking another test. Oh, chem exam. Eek. All right, good to know. I'll try to keep it as short as I can. How about? Because we're just going to finish chapter 4, or exponentials and logs. And so there's just a couple of things that I want to touch on, and then we'll leave the new stuff trig for next week. So, all right. Good to know. You guys have chem. Oof. Yikes. All right. With just 3 of you here, I can't really take a poll and see, because we had talked about having 3 tests and then you guys were kind of exhausted. So what I'll do is I'll post a poll on Moodle for what we want to do next. Okay, so don't worry about that. Focus on your chem exam. All right, so what were we doing? Oh yeah, section 4.4, because we finished 4.3 last day, and then I know you studied it for the test, so I'm not gonna do a review, but it'll come back up, so I'll kind of remind you as we go. Oh, and I had to write the note before I forgot, because I thought I had told you guys about 4.1 to 4.3, but then I had a couple of people emailed me saying, hey, I missed it. I'm so sorry. I've been swamped. So I know you've been swamped. That's okay. I'm happy to extend stuff if you guys are feeling like, oh no, I need some more time to work on this. So what I've done is 4.1 to 4.5, they're posted on Moodle, and they're due next Thursday, right? So a week from now at basically midnight, okay? And so I've extended 4.1 to 4.3. They're just quick little assignments, right? But I know usually the quick, easy ones are the ones who get put off. I've got bigger fish to fry. So so I've extended those, and you have a week to work on them, okay? So 4.4 is the laws of logarithms. Okay. Log laws, right? Or log laws. I don't know if you guys have watched Arrested Development, but Bob Loblaw's law blog. Anyways, it's always what I think of. So yeah, classic. So log laws are just laws of logarithms, and we use these laws to be able to solve for x, right? So some variable x. And so we use log laws, okay, to combine or expand logarithms, to combine or expand logarithms to ultimately solve for a variable. To ultimately solve for a variable, which is typically something like x. Okay. So what we have, these log laws, now let's see if, where did I put them? Functions, nope. Oh, there. So let's have a look at these. Oh, and I'm gonna pull that up. Where'd it go? it at the top. Hey. Crazy. All right. So what we have looks simple enough, right? We've got these 3 logs. And so what we need to remember is that these are the only things that we can do. So you'll see some scenarios where it might be tempting to combine logs, but we actually can't. So these are the only 3 things that we can do with logs. Surprisingly, it's enough, right? So the first one is that if you have A and B being multiplied inside a log, what you can do, so if you're multiplying, then what you can do is you can break them up, right, as the log with the same base, so log base A of A plus log base A of B. Now, of course, we can take it the other way, right, which might be useful, right? If you have logs of the same base, and that's important, right, then if you're adding logs of the same base, what you can do to combine these is to multiply them inside the same log, right? So here, if you want to combine them, then you're going from the right side over to the left side, right? And if you want to expand a logarithm, then you're going from the left side to the right side, right? So what I'll do here is, if you're going like this, you're combining, combine logarithms. Or if you're moving like this, then you're expanding logarithms. Expand logarithms. Oops, no M. There. Okay. So, same idea, right, is if you have the log of A, right, of A over B, so now we're talking about division, then the division, when we split it up, becomes subtraction, right? So the log of the same base that we had earlier, log base A of A minus log base A of B, we can combine these as division. Okay. And then finally, we saw this one last day, right? But we use it a lot. So if we have something in the power that we need to solve for, then what we can do is we can take the log base A, that's any log base, okay? So what we'll see is you don't necessarily have to have the same capital A base in your log as you do in your exponent to bring that down. It's just it makes it easier because you're able to cancel them. Right, but then what we're able to do is we're able to use the exponent's been brought down, or the power has been brought down in front, and now I'm able to solve for that power. Right? So we saw that last day, and we use that on the test. Okay? These 2 log laws are the 2 new ones. Okay, okay. So before we keep going, I also want to introduce the change of base formula. So if your calculator only has a log and ln button, right? So there's no, what does it look like on here? So if you have one that's kind of similar to this, or the gray version, you will have a log blank, blankety blank, no log base something. Yeah, so you should have that one because that's what the wet department says you should have, this type of calculator. So you have the special button, so you don't actually need it. But it is really good because what if you're working in industry and you don't have your trusty fancy calculator? Maybe you're just working on your phone or whatever. Your phone doesn't have the fancy button, and so that's okay. So if you're stuck and you don't have this fancy button, right, then we can use the change of base formula. The change of base formula to calculate logs of any base. Okay. So I'm just going to steal it from the notes here. The change of base formula, we'll write it out. Okay. Says that if you want log base b of x, okay, so log base 3 of 4, right, and you don't have a fancy button, then what you do is you pick some log base a, and log base a can be anything. So of course, if you only have the common log, log base 10, or the natural log, log base e, then you should be using log of a as one of these two buttons. I always use the natural log, right? It's easier to write. I think it's kind of the quickest one. And so as long as you're using log base a, which is the same for both of these, then what you do is you split up the log. So you have x going to the numerator, and then the base is going to the denominator. In fact, I'm going to move this down here and say here, you can pick any log, right? Use log base 10, which is just your LOG button, or log base E, which is your LN button. I always use the natural log. I always use the natural log. That's just a side note, right? But as long as you're consistent, then what you can pick anything, but you should use log base 10 or log base E if those are the only buttons that you have, right? So let's do a quick example here. Example, if you have log base 3 of 4, okay, and you don't have this fancy button, you can confirm it because you have the fancy button, then what you can do is you can say, okay, well, that's going to be the ln, in fact, I shouldn't write it like the button. Ln is usually how I write it, of 4, right? So whatever I'm taking the log of goes in the numerator, and then the base, the ln of 3 in this case, is going to go in the denominator. So I'll make a note here that this went here, and this went here. Okay. So if we check this, okay, the ln of 4 divided by, oopsies, divided by the ln of 3, I get roughly, so just a decimal approximation here, I get 1.2618595507, or using the log base whatever button. So just on your calculator, try log base 3 of 4. I get the same approximation, 1.2618595507, which is good, right? So it confirms that it works, right? And so if you're ever in a pinch, then just remember that you can use this change of base formula to write it out. Okay. All right. Let's do some work expanding and combining logarithms, just so we get the hang of it. And then we're going to move on to actually solving for x. Okay. So if we go to, let's see here. All right. So which ones do we want to do? Let's do 32 first. Okay. Or maybe we should start a little bit slower. Let's do 24 first. How about that? So 24 is log base 6 of 7r. Okay. So what I have here is I'm multiplying inside, right? Log base 6 of 7r. And so now, since I'm multiplying here, that is going to translate to addition, right? And so if I need to expand this thing, then this becomes the log base 6 of 7 plus the log base 6 of r, right? From those log laws that we copied in earlier, right? A is 7, B is r, and so now I can expand this, keeping the log base the same, right? That's important. And you can only combine them if you have the same base. Okay. So now let's do 32. Sometimes we have to do a little bit of work, right? So we've got log base 3 of x root y. Root y, right, is really y to the 1/2. So sometimes we have to do a little bit of massaging, right, to get it to look like something we can work with. Although here we're just multiplying x times root y, but later we'll be able to expand it just a little bit further using this last log, right? Y to the 1/2 we can write as 1/2 log base a, I can't remember what it was, of y, right? And so we're going to expand it completely. So log base 3 is what it was. Log base 3 of x root y. Well, I'm multiplying again, right here. Multiplying. So what I get is I get log base 3 of x plus log base 3 of root y. Okay. Here, root y is really y to the 1/2. Okay. So we can expand it even further and say, well, I'm going to rewrite this as log base 3 of x plus log base 3 of y to the 1/2, which I can expand a little bit further. Here, I'll bump it out a little bit. Log base 3 of x plus 1/2 log of y. Now, because I only have x's and y's, log base 3 of y. Okay. Why does it have this thingy here? Go away. Come on. Okay, I don't know what that is. All right. Good. So let's expand something else here. Let's maybe expand 40 looks good for a start, right? I want to do a little bit of division in there. And so let's do 40. Now I'll have enough for is log base a. Log base A can be anything, it doesn't matter. The log laws are all the same. X squared over y z to the 3. Now only z is to the power of 3, right? So what you're going to do is you're going to slowly pick this thing apart, okay? You've got division here initially, okay? So what you're going to have is now we've got division. So this becomes log base A of x squared minus, right, because we're dividing, so we subtract the whatever is the log of the denominator. So log base A of y z to the 3. Okay. Keeping in mind that, okay, it looks like we can expand this a little bit further, but this minus is outside of this whole thing, right? And so what we have, and I'll make a note here. Okay, so here we've got a power, and here we've got multiplication. Okay. So to expand this completely, what we're going to have is I'm going to bring this power down in front. That's just a log law that we need to have a really good handle on, right? Even if the x isn't in the power, if I want to expand this as much as possible, then I bring this 2 down in front. So I get 2 times the log base A of x minus, and now because I'm going to expand this multiplication, right? If I'm multiplying inside, I can expand it by adding, so log base A of y plus log base A of z to the 3. But I need to make sure that they're both being subtracted, right? And so what I'm going to do is I'm going to put a big bracket around here. So we've got log base A of y plus log base A of z to the 3. Okay. There's one more, right? So here we just have x, great. Here we just have y, great. Here we have z to the 3, so we can expand this power. Okay. And we can expand this negative inside, right? So we have 2 log base A of x, that's expanded as much as I can, minus the log base A of y, minus 3 times the log base A of z. Now this is completely expanded. Last one I want to do is, of course, 47 of these ones, and then we're going to combine all of them, kind of smush them back together. But as long as we have a really good handle on those 3 log laws, we can manipulate these things a lot, right? And so let's have a look at 47. We've got the log. Because there's no base, it's assumed that it's the common log, log base 10, right? And so we can just use log, but the log laws are all the same. The base doesn't actually matter. The log of the root of x squared plus 4 divided by x squared plus 1 times x to the 3 minus 7 squared. Okay. This is all inside the log. Okay. All right. So first thing I'm going to do is I'm going to deal with this square root. There's nothing really that I can do here. I could put the square root on each of these. That's fine. That's an option. Or I can put the square root all outside. It's really just a matter of preference, right? Because as long as I put the square root over each of the lumps here, so we have 2 options. Oops. 2 options. right? We could write that the root of x squared plus 4 over x squared plus 1 times x to the 3 minus 7 to the 2 is the same as the root of x squared plus 4 divided by the root of x squared plus 1 times the root of x to the 3 minus 7 squared, which would of course cancel with that square root. Okay, so that's one thing, just using the properties of exponents. A square root is just the power of 1/2, right? So properties of exponents say that I can split the exponent over division, right? And as long as I'm multiplying down here, right, I'm multiplying x squared plus 1 by x to the 3 minus 7 squared. So as long as I'm multiplying, I'm allowed to split up the root, right? I can't do the root over x squared plus 1. I can't split it up. Only multiplying and division, I can split it up, right? So, or same deal here, x squared plus 4 over x squared plus 1 times x to the 3 minus 7 squared. Well, I can write that all as x squared plus 4 divided by x squared plus 1 times x to the 3 minus 7 to the 2, all to the power of 1/2. Okay. It doesn't matter which one you use. In fact, I'm kind of torn. I don't know which one I prefer. Maybe I'll use this one because then I can move the 1/2, right? Because then if we treat this as one thing, let's call it a, right? Technically, all I have here is the log of a to the power of 1/2, right? So then I would take the 1/2 and then I have 1/2 log a, right? So letting x squared plus 4 over x squared plus 1 times x to the 3 minus 7 squared equal a, right? We have the log of a to the 1/2, which by that third rule says that that's the same as the 1/2 log a, right? If you prefer to use this one, that's fine, right? But then you'd have to remember that, okay, I've got a power of 1/2 on each of these, except for this one because it would cancel, right? The square root of a square is just itself, right? And so, but let's use this one because then we can get that square root out of the way. Okay. So what we can do, let's write it out again here, is that we've got the log of the root of x squared plus 4 over x squared plus 1 times x to the 3 minus 7 squared is the same. So from up here, I've already shown it. And so that's the same as 1/2 times the log of everything inside, right? This fraction, x squared plus 4 divided by x squared plus 1 times x to the 3 minus 7 to the power of 2. From up there. Okay, so now, keeping in mind that I can only expand, right, if I'm multiplying or dividing. So this addition up here, there's nothing I can do, right? But I'm dividing x squared plus 4 divided by this denominator here. And so I can split those up, right? Remembering that it's all times 1/2, okay? So this becomes, and I'm gonna scoot it over, 1/2 square brackets, just because the 1/2 is all outside of everything. The log of x squared plus 4 minus the log of everything in the denominator of x squared plus 1 times x to the 3 minus 7 squared, and square brackets. Okay. So not sure why this keeps popping up, but whatever. I think I rest my hand on it. There's nothing I can do here, right? X squared plus 4, there's no multiplication, there's no division. And so I'm just adding x squared and 4. So there's nothing more I can do, right? And sometimes that's the end of the road. Right here, I'm multiplying. So I can expand that out a little bit, right? Treating x squared plus 1 as if it's a, and x to the 3 minus 7 squared as if it's, say, b squared, right? Or b if you want. So what we get, again, we've got this negative on the outside. So you need to be so careful with all your brackets here. And so what we have is 1/2 times the log of x squared plus 4 minus, and I'll put a bracket here, the log of x squared plus 1 plus the log of x to the 3 minus 7 squared. So many brackets. Okay. There's nothing I can do here. X squared plus 1, there's no multiplying, there's no dividing, right? Here, I do have a power, right? And it's the power on the outside. So I can bring it down. And I'll scoot this up so it all fits on the same page, hopefully. There. Keep that 1/2 on the outside. Maybe I won't fit it on the same page. Keep that power on the outside, or the 1/2 on the outside, just until you're done inside, and then you can bring it in. Okay, so this becomes the log of x squared plus 4 minus the log of x squared plus 1 minus 2 times the log of x to the 3 minus 7. Right? I brought that power of 2 down in front. Okay, and I also expanded, and I'll make a note of that. That negative has to expand inside. Okay. So now I have 1/2 times the log of x squared plus 4, right? And so minus 1/2, and then minus 2/2 is just going to go away, right? Minus the log of x to the 3 minus 7. So what we have is we have 1/2 log of x squared plus 4 minus 1/2 the log of x squared plus 1 minus the log of x to the 3 minus 7. I'm not showing the 2/2 canceling to 1 because I am at the end of the page. Good. So that's expanding. Now we're going to do the same thing, but we're going to combine these or kind of contract them. Okay. So we'll start with 50. Okay, so now I'm going to combine this thing, right? Just kind of contract it. What you'll see, it's more common that we have to combine things, but being able to expand and combine, they're just opposites of each other, right? So we need to be really, really flexible, moving back and forth, and kind of knowing these log laws so that we can manipulate something if we're solving for x, for example. So here, right, if you have x squared minus 1 and x over here, and you're trying to solve for x, well, of course, you would want to combine these if you can so that you can kind of shake out the x. Okay. But let's start with 50, nice and slow. 1/2 log base 2 of 5 minus 2 log base 2 of 7. Okay. First thing we can do is I can bring this power upstairs, right? The 1/2 is the same as log base 2 of 5 to the 1/2. Okay. So this can go here, and this can go here. So I have log base 2 of 5 to the 1/2 minus the log base 2 of 7 to the 2. Okay. Notice that these are the same base, and I'm subtracting same base and subtracting. So to combine this, to kind of accordion it up, we have log base 2 of 5 to the 1/2 divided by 7 to the power of 2. So we get log base 2 of 5 to the 1/2 divided by 7 to the power of 2. And you can simplify that, right? That's the root of 5, and then 7 squared is 49. Does it work out to anything? Root 5 divided by 49? No. So, or log base 2 of root 5 over 49. If you stopped here, I'd be fine with that, right? So let's do one with some x's in them. No, let's do 52, a little bit harder. 52. 3 natural log of 2, or I just call it the log, but I know that's confusing. 3 log 2 plus 2 log x minus 1/2 log of x plus 4. Okay. Step 1, in my mind, at least, is I put the powers all back on, because until I have just the log of the same base, I'm not able to combine things. And so I'll just make a note here. This is going to go here, this is going to go here, and this is going to go here. Okay. So this becomes ln of 2 to the 3 plus ln of x to the 2, put these inside, minus the ln of x plus 4 to the 1/2. Okay. If you think about it, what if you brought this negative 1/2 up top? That's the same as saying 1 over x plus 4 to the 1/2, right? Which is what puts it in the denominator in the first place, right? So division here is because you've got a negative exponent. So you really only need the addition, right? The multiplication becomes addition law, and then the second one falls out. But it's probably easier right now to just think of them as separate things. Okay. So now I'm adding and subtracting. Okay. It doesn't actually matter which order you do these in, but maybe it's easier to just do the addition ones first and then do the subtraction. So I have the ln of 2 to the 3. Of course, I have to make sure I have the same base. Because I have ln, I'm safe, right? So ln of 2 to the 3 times x squared minus the ln of x plus 4 to the 1/2. Okay. So now I'm subtracting here, which means it's going to become addition. So I have the natural log of 2 to the 3 x squared divided by x plus 4 to the 1/2. Which is the same as the ln of 8x squared divided by the root of x plus 4. All right. Notice that what we were doing before was just going from something like this back to something like this. So we're just moving back and forth, back and forth. Let's do, which one should we do next? That one's similar. Let's do 55 because it's a little bit weird. Okay. 55, so we have the natural log of a plus b plus the natural log of a minus b minus 2 natural log of c. Same setup, right? Except we don't have any powers except for this last one. And so what we can do is we can say, okay, well, I'll combine these, just double check you have the log of the same base. And so ln, okay, we can combine these. And so we have the ln of a plus b times a minus b minus the ln of c squared. Okay. Or if you want, plus the ln of c to the -2. That works as well, but that's the same as c to the -2 is the same as 1 over c squared. Then I'm multiplying by 1 over c squared, right? So that's just a side note. I think it might be easier to just go from subtraction to division. So what we get is we get the ln of a plus b times a minus b divided by c squared. You can leave it like this. You can expand the numerator out if you want to. I'm not going to. I don't really see anything canceling, so with the c squared, so, well, because there's no c in the numerator. Okay. So, good. Okay. Guess I should, I've been putting it on a fresh page, so. Section 4.5. Or maybe what I'll do, let's just do, because we've got some space here and we only did one example of changing the base. And I've got a couple here. Why not? So remember the change of base formula is that log base A of B is the same as, or what was it? Log base, sorry. Log base B of x is the same as, there's the log base A of x over log base A of B. So let's just do 63 and 66, just so we get the hang of it. Log base 7 of 2.61 is the same, and so here, like I said, you can use any log, probably log base 10 or ln, just because those are the only buttons you have typically. So I'm going to use ln. So ln of 2.61 divided by the ln of 7, right? Whatever is inside the log goes on the numerator, and the base of the log that you want goes in the denominator. How about 66? Log base 12 of 2.5. Well, it's just going to be the natural log of 2.5 divided by the natural log of 12. And you can confirm it using your calculator. Good. Now let's talk about 4.5, which is just kind of the grand finale here, exponential and logarithmic equations. So if we need to solve for x and it's in the exponent, right? So if it's in an exponential equation or if it's in a logarithmic equation, we need to be able to solve for x. So we need to be able to solve, for x if it is in an exponential or logarithmic equation. So the steps kind of, you would probably arrive at this on your own. But if we start with the exponential equations, what we need to do. So if we're solving exponential equations, so something like a to the power of x, and we have to solve for x, you have to isolate the exponential expression on one side of the equation, right? So you basically move x to one side, which is what you would do anyways, right? Then you take the logarithm of each side and then use the log laws to bring down the exponent, right? And so we did that just briefly, but now we're going to make our exponential equations a little bit bigger. And then once you've brought down your x, you can solve for it. Okay. So let's see here. Let's do 14 first. Okay. So 14 is e to the 0.4x is 8. What we were doing before was we just took the log of the same base as the base of the exponent. In this case, because it's e, I'm going to use the ln, but what you'll find is that I'll probably always use ln unless it's an easy base to cancel, right? And so I usually use ln to bring down any exponent. It doesn't have to be the same one as the base. So what we have is I'm going to take the ln of both sides, e to the 0.4x. Oops. ln of 8 is just the number, which you can calculate on your calculator, right? But when I take the natural log of the natural exponent, right, exponential function, then the power just drops down, right? So this becomes 0.4x is ln of 8. Solving for x, right? What I have to do is I have to divide both sides by 0.4 to get x on its own. So I get x is the ln of 8 divided by 0.4. Okay. This is the exact answer, right? So here This is the exact answer. And the approximate answer, ln of 8 divided by 0.4, is roughly 5.1986. This is the approximate answer. Okay. So here, find the exact solution, and I didn't even realize that it was asking for both, but so sometimes, often I'll just leave it as the exact answer, and then sometimes I'll ask you for the approximate answer rounded to some number of decimal places. Here rounded to 6 decimal places. I guess I wasn't even paying attention. I can do that. 1, 2, 3, 4, 5, 6, 104. Okay. So we've solved for x even when it's hidden in this exponential function, right? Using the laws of exponents and logs. Okay, let's do, I want to do one. Let's do 16. Because I want to do one that doesn't have the e in it. E makes it easy to pick the natural log. But I just want to show you that you don't have to use log base 3 to solve something like 16. So we have 3 to the, now where did it go? 16, here. 3 to the 2x minus 1 is equal to 5. Okay. We can use any log to bring down the power. So what I'm going to do is, even though I could use log base 3, right? Log base 3 of 3 is 1. 3 to the power of what equals 3? Well, it's 1, right? And so log base 3 of 3 would cancel out. But if I don't care about that, then what I can do, and most commonly, I just take the log of both sides, and by that I mean the natural log. So the ln of 3 to the 2x minus 1 is the ln of 5. 2x minus 1 is all in the power, so it all gets shifted downstairs, which is going to be 2x minus 1 times the ln of 3, which is the ln of 5. Keeping these separate, I'm not going to expand them out. You can, right? But what I'm going to do is I'm just going to keep 2x minus 1 on its own, and the ln of 3 I'm going to divide over to the right-hand side. So what I get is I get 2x minus 1 is the ln of 5 over the ln of 3. Solving for x, right, I have to first add 1 to both sides. So it gets a little bit mucky, but that's okay. And then I have to divide both sides by 2. So I have 2x is the ln of 5 over the ln of 3 plus 1. One thing that you could notice is that this is the same as log base 3 of 5, right? If you use the reverse change of base formula. We could use the reverse. I don't really see a point in doing that, but I'm just highlighting that we have options as we go along. So we could use the reverse change of base formula. To write ln of 5 over the ln of 3 is the same as the log base 3 of 5. Which, if you go back here, right, we would have to take the log base 3 of both sides. So log base 3 of 3 becomes 1, and log base 3 of 5 is what we have here. So they're always connected, and we always have options. And then, but I'm going to leave it. I'm just highlighting that we could do something like that. Then I'm going to divide both sides by 2. So I get x is the ln of 5 divided by the ln of 3 plus 1, all divided by 2. I guess I could leave it like this. We could simplify a little bit more. But what I would need, right, is I would need a common denominator here. So I'd have to do 1 times ln of 3 over ln of 3. And then I've got a fraction over a fraction. Let's see if we kind of get anywhere here. So x is the ln of 5 over the ln of 3 plus 1 times the ln of 3 divided by the ln of 3 divided by 2. X is the ln of 5 plus the ln of 3 divided by the ln of 3, all divided by 2. Hey, what? This worked out nicer than I anticipated. But now, so we're adding logs of the same base, which means I can multiply them together, right? And so it's the ln of 5 times 3 divided by the ln of 3. Ln of 5 times 3 over the ln of 3 divided by 2 divided by 1. Right here, I've got a fraction over a fraction. So now, right, 5 times 3 is, of course, 15. So I have the ln of 15 divided by the ln of 3 times 2 over 1 becomes 1 over 2. So x becomes the ln of 15 divided by, okay, so now I've got 2 times the ln of 3 by the power laws vested in me. I can write this as 2 log of 3 just so we can see it, right? But then I can also bring this on top. So x is going to be the ln of 15 divided by the ln of 3 to the power of 2, which we can simplify. The ln of 15 divided by the ln of 9. And now we're done. Okay, there's nothing that we can do here. Remember, the log laws only work for adding or subtracting if you're trying to combine them. So even though it looks like we could combine things here, we can't. So, good. That's a lot of work, right? But knowing those log laws is going to help you out. Okay, so that was 16. That's, of course, the exact solution. I'm going to leave it at that. Okay. Oh, I guess we could write this, could get fancy. We could write this as the log base 9 of 15. By that same kind of reverse change of base formula. But I'm not expecting to see that. Once you're here, I would say you're done. Okay. Let's see here. See the one we did. Okay. Let's do 27. So we have 4 times 1 plus, 10 to the power of 5x equals 9. Okay. So what I have to do is I have to isolate this exponential function, right? So I need to pick away until I just have the exponential function, which is what I can take the log of. And so that means I have to shift everything else over to the right-hand side. Need to isolate this in order to take the log. Okay. So order of operations says that if I have 4 multiplying everything, I have to divide both sides by 4 first. So I have 1 plus 10 to the 5x is 9 divided by 4. Then if I'm adding 1, I have to subtract 1 to both sides. So I have 10 to the 5x is 9 over 4 minus 1. So now that I've isolated this exponential function, I can take the log. And in this case, I'm going to take the log base 10 because it makes it nice and it cancels. So I take the log, log of 10 to the 5x is the log of 9 over 4 minus 1. You could put this over a common denominator, right? Subtracting fractions and just have one log in here. I'll probably just ignore it for a little bit longer. So now I can bring this power down. Just by the log laws. And so I have 5x times the log of 10. Okay. Log base 10 of 10 is 1, and you can try it on your calculator. And so here, log base 10 of 10 equals 1, which is the log of 9 over 4 minus 1. Again, we could simplify that inside the log, but for now I'm just going to leave it. So what I get is I get 5x is the log of 9 over 4 minus 1. So x, if I divide both sides by 5 to shake out the x, I get log of 9 over 4 minus 1 divided by 5. I'd probably leave it like that. Right? We could simplify this. Nine over 4 minus 1 is the same as 9 over 4 minus 1 times 4 over 4, which is 9 minus 4 over 4, which is 5 over 4. Right? And so what we could do if we wanted to, we're going to get the same number. So if you're going for a decimal approximation, you don't have to do that simplification, right? But what we get is we get x is the log of 5 divided by 4 over 5. We could expand this, right? That's the log of 5 minus the log of 4, right? If I'm dividing inside, then I can break it out. Right, so it just depends on if your calculator, if you want to do 5 over 4 and then the log of it, or if you want to do the log of 5 minus the log of 4. So, or if we want to, x is the log of 5 minus the log of 4, all divided by 5. Okay. So let's do let's do 38. Ten divided by 1 plus e to the negative x equals 2. Okay. So I need to isolate the e to the negative x because I'm trying to solve for x. Actually, I'll move this, say that up above. So laws of exponents, or sorry, just order of operations is what I wanted to say. It says that I should, if I need to isolate 1 plus e to the negative x, I can multiply that over to the other side, and I get 10 is 2 times 1 plus e to the negative x. From here, I can divide 2 over to the left-hand side, right? And then subtract by 1. So 10 divided by 2 is 1 plus e to the negative x. Okay. So 5 minus 1 is e to the negative x. 10 divided by 2 is 5. Then I have to subtract 1 from both sides. So I did 2 steps in one here. And we should be getting more comfortable with this anyway. So 5 minus 1 is, of course, 4. Is e to the negative x. Now that I've isolated e to the negative x, I can take the natural log because I have this nice e. The natural log of e is 1. So I take the natural log of both sides. I have to do it to both sides, right? Times the natural log of e to the negative x. The log law says that this negative x goes down in front, and that's how I'm going to shake it out. So I have the log of 4 is negative x times the log of e. Log of e is just 1. Log base e of e is just 1 because e to the power of what equals e? Well, it's 1. So now I have the natural log of 4 is negative x. Okay. I always like to have what I'm solving for on the left-hand side. So remember, an equal sign, a equals b is the same as b equals a. So I'm allowed to just switcheroo here. But in my switch to moving x to the left, just because that's where I like to have it, I'm also going to take the negative of the log of 4. So this becomes x is the negative log of 4. Good. You could simplify this if you wanted to. Right, the negative log of 4 should be the same as the log of 4 to the negative 1, which is 1 over 4, so the natural log of 1 over 4. You can try it. Or the natural log of 4 to the negative 1, which is the natural log of 1 over 4. Okay, so try the natural log of 1 over 4, and then try the negative natural log of 4, and they should be the same. So it doesn't matter. Okay. So we can do the same thing for solving logarithmic equations. Solving logarithmic equations, we isolate the log, right? Basically whittle down to x as far as you can. Right? So you isolate the logarithmic term on one side of the equation. I like to have it on the left. And just as a heads up, you might first need to combine the logarithmic terms. Okay, so that's why we need to be really good at combining logs and then write it in exponential form. So from a log to undo a log, we use the exponent. To undo exponents, we use logs, and then solve for the variable. So let's grab some of these here. Which one? We'll do some of these. Oh yeah, this one would be good. Let's do 50 together. So I've got the log base 5 of x plus the log base 5 of x plus 1 is equal to the log base 5 of 20. Now, first thing I'm going to scan, do I have the log of the same base here? Yes, I do. Okay, so then I know the log laws are available to me. What I'm going to do is I'm going to combine everything on the left-hand side. Okay, because I'm adding logs of the same base, I can smush them together by multiplying inside that log. So here I get the log base 5 of x times x plus 1, which is the log base 5 of 20. Okay. What's nice is that, okay, if I have the log of 5 of a is equal to the log of 5 of b, because I have the log of the same base here, they essentially cancel out, right? I would take 5 to the power of both sides, but they would cancel out. And so there's a cancellation property that says, I'll put it over here. Maybe I should write it in pink instead. It's important. Note, log base a of a, if it's equal to log base a of b, then a must be equal to b. Okay, so if you have the same logs here, but they have to be all combined, so you can just have the log base a and log base a on both sides, then you can drop the logs and just say, well, then a must be equal to b. Right? Kind of intuitive, right? But we need to say it. So then what we have is we have x times x plus 1 is equal to 20. All of a sudden, I'm just dealing with a quadratic, right? I can expand this thing out and I know how to solve quadratics. So I get x squared plus x is equal to 20. Okay. I can subtract 20 from both sides, so I get x squared plus x minus 20 equals 0. This is just a quadratic equation. So we can use the quadratic formula to solve. Dang, this quadratic formula keeps popping up everywhere, right? Quadratic equations, so we can use the quadratic formula to solve for x. Okay. So we have x squared plus x minus 20 equals 0. Here, a is 1, b is 1, and c is negative 20. So x then, x is going to be negative b plus minus the square root of b squared minus 4ac over 2a. Plugging in my values, it's just a plug and chug situation here. So negative 1 plus minus 1 squared minus 4 times 1 times negative 20. Divided by 2 times 1. So I get x is negative 1 plus minus the root of 1 minus negative 80, 81, which should be 9. So x is negative 1 plus minus 9 divided by 2. So x is going to be negative 1 plus 9, and I will use my calculator because I don't want to screw this up. The square root of 81, just confirming that it's 9, it is negative 1 plus 9 divided by 2. It's 8 divided by 2, which is 4. And x is negative 1 minus 9, negative 10 divided by 2, negative 5. But, okay, there is a restriction, or there are restrictions on the domain in a log, okay? So here, we can't take the log of anything but a positive value, right? So x equals 0 can't happen, and we can't take the log of a negative number. So because we have just log of x here, and then we have x plus 1, we need to remember that we can't take the log of a negative number. So here, in red, because it's important, we can't take the log. So negative 5 is a solution to that quadratic, but we have to extend it to the log. So we can't take the log of a negative. So x equals negative 5 is not in the domain. Therefore, x equals 4 is the only solution. Okay. So that's important to keep in mind, right? I'll admit, sometimes it's hard to remember, oh, I can't have a log of a negative number, but you should always check your solution to make sure it works back in the original equation. Okay. So let's do I'll leave those ones. We did that one, and they're all kind of similar. Oops. Let's do another one. Maybe they're all the same. They all do the same thing. Let's do one. They all work out to basically shoot, I should have had one up my sleeve here. Let's do 66. So I've got the ln of x minus 1 plus the ln of x plus 2 equals 1. Okay. So I can combine this because I'm taking, oh, I wanted to do, sorry. Do you see what happens here? X minus 1 times x plus 2 becomes a quadratic, and then I solve a quadratic equation again. I wanted to use a subtraction one. So just forget 66. You can do that one. It's the exact same as what we just did. Let's do 67 where there's subtraction instead. The log base 5 of x plus 1 minus the log base 5 of x minus 1 is equal to 2. Yeah. So what I can do is I can combine this into one log. That might make things easier, right? And so here what I'm going to do is I've got subtraction, and so I've got the log base 5 of x plus 1 divided by x minus 1 is equal to 2. Okay. So let's see here. Log base 5, I could take the power, any power, but what I'm going to do is I'm going to raise it to the power of 5, the same base, because the 5 to the power of log base 5 is going to cancel out, and just what's inside is going to drop out. But that also means I have to have 5 to the power of 2 on this side. So I have 5 to the power of log base 5 of x plus 1 divided by x minus 1 is 5 to the power of 2, right? So you use the same base that you have in your log. That means this side is going to cancel, right? That's going to basically cancel out. And so what you have is you have x plus 1 divided by x minus 1 is 5 squared, which is 25. Solving for x here, right? We could take a little bit of time and see if we can factor this. Sometimes it's easier if you factor, but I'm just going to multiply the x minus 1 over to the right-hand side. I think that's the easiest in this scenario. But keep an eye out for factoring. If you're able to factor, that might make things easier for you. But I don't like factoring, so I'm just going to move it over. 25 times x minus 1. Okay. So if I'm solving for x, right, now I'm back to this kind of small equation that we're very used to working with. So x plus 1 is 25x minus 25. Right, because if I'm solving for x here, I need to collect like terms, which means I have to move my x's to one side and everything else to the other side. So kind of in one quick move, I'm going to add 25 to, I'm going to subtract 1 from the right-hand side, and I'm going to subtract 25x from the left side, only because I want to have the x's on the left. Doesn't matter which order you do. So x minus 25x is negative 25 minus 1. Putting me at x minus 25x is negative 24x. Negative 25 minus 1 is negative 26. So x must be negative 26 over negative 24. Surely that simplifies, and your fancy calculators will just do it for you. First of all, a negative divided by a negative is a positive, right? So 26 divided by 24, 13 over 12. And I'm just going to leave it as the exact answer. Double check, right? 13 over 12 is your x. Just make sure that 13 over 12 yields positive values, right? So 13 over 12 as a fraction is 1.0833. 1.08 plus 1 is greater than 0, great. 1.03 minus 1, phew, just under the wire is also positive, so we're safe. Right. X equals 13 over 12 is in the domain. So it is a solution. Woo. So we're going to use these for word problems a lot of the time. Hey, what happened? Okay, weird. Hey, it deleted my note. X equals 13 over 12 is in the domain. I just wrote that. So it is a solution. Not quite as exciting this time. Okay. So like I said, we're going to be using these to solve a lot of word problems, just quick little word problems. We're not going to build these formulas or anything, although we could. Let's talk about 93. How long, so now we're talking about time, how long will it take for an investment of $1,000 to double in value if the interest rate is 8.5% per year compounded continuously? So compounding continuously, if we have, and I've got the little equations here, the formulas. Over here. Here. So if we're compounding continuously, A of t, which is the amount after time t in years, is p times e to the rt. It's kind of there. So what we have, the formula that we're using, compounded continuously, A of t is p, which is the principal, times e to the rt. Now, if we want $1,000 to double, the principal amount is 1,000 and A of t must be 2,000, right? The double of that. So we have 2,000 is 1,000 times e, and then the rate as a decimal, right? 0.085. Can make sure, divide it by 100, 0.085 t. Solve for t. Okay. If I'm trying to solve for t here, again, I've got this exponential function that I need to isolate. So I need to divide both sides by 1,000. So I get 2,000 divided by 1,000, which is just 2, is e to the 0.085 t. If I take the natural log, then the natural log of e is going to cancel out. So I take the natural log of 2 is the natural log of e to the 0.085 t. This is going to transfer down, and the natural log of e is just 1. So I get the log of 2 is 0.085 t. Solving for t, and also doing a little switcheroo here, t becomes the natural log of 2 divided by 0.085. Because we're talking about years, it's hard to communicate, oh, it'll only take the log of 2 over 0.085 years. So that's the exact answer. Approximately, we have the natural log of 2 divided by 0.085, which is roughly 8.15 years. Okay. The last problem I want to do is this kind of multi-part problem of the fish population. So a small lake is stocked with a certain species of fish, okay? The fish population is modeled by this function, right? So we've got this exponential function down here, where P is the number of fish in thousands, and T is measured in years since the lake was stocked. And we're gonna find the fish population after 3 years. So that's the type of problem that we were solving earlier. But then now we can also find after how many years will the fish population reach 5,000 fish. Remembering the units here, so paying attention to the units, thousands. So 5,000 is just going to be 5, right? So just be careful with your units. So A, let T be 3 years. So P of 3 is 10 divided by 1 plus 4e to the negative 0.08 times 3. This is just a matter of solving it, right? And just going through and simplifying negative 0.08 times 3, e to the power of whatever you found times 4 plus 1, and then divide by 10, or 10 divided by that. So we get negative 0.8 times 3 puts me at 10 divided by 1 plus 4e to the negative 2.4. E to the negative 2.4, e to the power of the answer button. So I like the answer button on this calculator. Just plugs in your previous answer, so you don't have to retype it. 10 divided by 1 plus 4 times, and here now I'm in decimal approximations, that's okay, 0.09071795329. Multiply that by 4. Just going through and showing all the work in the order that you should be doing it, right? So 10 divided by 1 plus 0.3628718132, and plus 1. 10 divided by 1.3628718113, 2 presumably. 10 divided by that answer, I'm at 7.337447222. The fish population after 3 years in thousands is 7.337, right? In terms of fish, right? The population after 3 years is 7.337 thousands, or approximately 7.337. Just multiply it by 1,000. And then B, after how many years will the fish population reach 5,000 fish? Well, we already know at 3 years we were at 7,337, so it's definitely going to be less than 3 years, and we can use that as a little check-in point, right? But 5,000 fish is a P of 5. 5,000 fish means we're going to let P equal 5. So then if we copy out our equation, because it's not on the same page anymore, 10 over 1 plus 4e to the negative 0.08. Sorry, it's just 0.8. Yeah. My first time screwing that up. Good. T. So we let 5 be equal to 10 divided by 1 plus 4e to the negative 0.8. T, and we're going to solve for T. again, I need to isolate the t. There are a couple of ways I can do that. I'm going to move this whole denominator, I'm going to multiply it over to the 5, right? But keep them separate. So what that looks like is I get 5 times 1 plus 4 e to the negative 0.8 t is equal to 10. Keeping them separate, right, makes it easy to bring this 5 over to the right-hand side. Okay, so I'm isolating t, I'm kind of picking away at it. So I get 1 plus 4 e to the negative 0.8 t is 10 divided by 5, which of course is 2. If I do 2 and then subtract 1, I get 4e to the negative 0.8 t is 2 minus 1. I'm trying to get the exponential on its own, so I have to divide both sides by 4, so I get e to the negative 0.8 t is 1 divided by 4, and I'm trying to keep it on the same page here before we end. So if I have to bring this exponent down and I've got an e, the natural log is my natural choice. So are we ready to bring down that power in the first step? So here we go, picking up a notch. Negative 0.8 t times the log of e, which you don't even need to show because it's 1, is the natural log of 1 over 4. Trying to solve for t, right? Log of e is 1. Okay. So what we get is we get t is the log of 1 over 4 divided by negative 0.8. So t is approximately, and you can break this up, right? The log of 1, or the natural log of 1 minus the natural log of 4, it just depends on what you like. So the natural log of 1 over 4 divided by negative 0.8, t should be positive, right? Time should be positive. And I get roughly 1.73286791. It will take approximately 1.73 years. Nice. Rigorous log law day, but now we're done with exponents and logs, but you do need to practice it quite a bit. But I know you have your chem exam, so I'm going to let you go unless you have any questions for me. But I'll stop this recording.